Now we will going to discuss theory of arrays. So theories of arrays is about handling something like AX, which you must have seen in your programming languages, where this object is called arrays and you may access using some indexing type object. These arrays are ubiquitous in our programming languages. In Python they may be called a dictionary, but the concept of arrays is everywhere. If we want to reason about programs, we should be able to support arrays in our solving engines. So now we will see that an axiomatization of the arrays and an abstract understanding of the arrays such that we can analyze all sorts of arrays occurring in various contexts. There will be three key points which we need to remember is that we will say that arrays is accessible by two functions. One function is the read function. Okay? Basically square brackets let you read an array at a particular point. Another is a store. You can point twice. You can update a value in somewhere in the array, and you can update an array and read from the array at a single point. You cannot just read the whole array at the same time or change the whole array at the same time. That's the key restriction of the arrays. And as far as abstract model is concerned, there is no length of the array. We assume that this is unbounded length. Whatever the size of the data type of indexing is, that much that big that array is. We can model the length of the array very easily on top of this abstract model. That is not fundamental difficulty in modeling arrays. However, to be compliant with all sorts of usage of arrays, people have chosen this abstract understanding of arrays. So remember that if you have studied a first order logic in your undergraduate or somewhere, then you likely have learned arrays without sorts. Okay. However, we need to have sorts here in this case because arrays themselves are a certain type, and the indexing has certain type, and the values that are stored in the arrays may be of different types. For example, you can have an array indexing which basically integers, and the value stored as strings, or the other way around. You have integers are stored, indexings are strings. This theory lives in a many sorted first order logic, and the model has a domain that is partitioned into values of each sort. So if you're not entirely clear about it, please take a look at many sorted for that. Okay, so let's try to understand these two functions that access our arrays. Okay, the first is this read operator. It takes two parameters, parameter 1, parameter 2. One is an array and other is index, and it returns a value. The other function is store, which takes three parameters: array, at index, which index you want to read, and the value you want to write. So notation, you can see that it returns an array. When you write on the array, it does not modify in place that array. It reduces another array which has this updated value. Since this is a logic, there is no actually copies being made. Is just for our understanding and writing down the formula that have some well-defined semantics. So what would be our signature here? So we will have one function which takes two parameters, another function which takes three parameters. They are no predicate, and equality is we assume that is a part of first order logic syntax. So what is the theory? Theory consists of signature and a set of axioms. So we need axioms now. So what axioms would define an array? If you write at the position I on array A, okay, value V, then this will produce another array, right? Let me call A prime. If you write A prime at index I, it should return the same value which I have just written. Okay? That's the property of read and write. So that's a very basic idea. Second is also very similar. It says if I is not equal to J, okay? And if you had written at value position I and you read at position J, now J is different from I, therefore it's not same position you're reading, so it should return the same value which A would have written. Okay, so it is simply saying if you write position I, the value of position J does not change. Finally, the third axiom says that if two arrays are not equal to each other, then there must be some index at which they are not equal. One important point to make is that this has a extensional quantification. Therefore, it introduces a Skolemization step. Its presence makes and reasoning over the array is difficult and maybe undecidable. And therefore, this third axiom has several versions, and you can look at references where these versions are discussed. And the one which is written here is called extensionality axiom, and there are other which are called non-extensional theories of arrays. So what is a model of this theory of arrays? Okay? So you have a model consists of model of your indexes, okay, and then you have a set of values that are produced in the value domain, and also set of arrays which are constructed to use indexes and these values, okay. So like how many different possible arrays are there for given indexes and value set, okay. Basically all possible functions which can take values from indexes and return you values from this value set. Consider the following formula and let's build the satisfying assignment for this formula. Let index m be 1 and 2. So we're saying that my indexes have only two values, 1 and 2, and my value set has only 3 and 8. Right? So I may claim that there are 4 possible arrays. How? Let me construct all possible choices. One possible choice is 1. If you give 1, it returns 3, and when you give 2, it returns 3 again, and 8 returns 8, 8, 3, 8, or 8, 3, all possible combinations. So if you write on array A1 at position 1 value 3, then what will be the output value, because it will produce the same array again, okay. If you write 8 at position 1, now its value stored is 8 and 3, and 8 and 3 is this guy, so probably you will return 8, 4. Similarly, you can do the exercise and then see, get a sense that each time you write, you produce another array from the domain of arrays. Now let's get back to our formula. Okay, so we had a of I equals to a of j, and I is not equal to j. So how do I make I not equals to j? There are two indexes, so one of them 1, another one is 2. So I is, let's say from our set of indexes is that 1, and j takes the value 2. So we are saying it should be ai equals to a2, and we should choose an array which have both outputs are same. Maybe we can choose a1, so we can say a equals to a1, and that will be the model of your formula. So it assigns a value to each of the variables that are appearing in your input formula, and also all the arrays appearing in your theory of arrays is undecidable. However, the quantifier free fragment is decidable and often used in analyzing in programs. So let's see how would you check satisfiability of a formula. Now this will give you some intuition how the reasoning is going to work out. So let's suppose I give you this formula and I ask you this question, that is it sad or unsad. So to prove that, you need to apply the axioms and derive facts, and maybe there is a contradiction to derive unsatisfiability. So if you apply axiom 3 on your problem, then you will see that if a is not equal to b, there must be an index j such that you can have a disequality. Okay, so you apply that, and now you have a new symbol j. Now we carry on, and then due to congruence, you can apply j on both sides and you get the same output, because these both terms are equal. Therefore apply any function on it, it will give the same output. So therefore if you read j at the index j, it will give the same output. This is not application of the axiom, it is due to congruence. Okay, now we apply our axiom, other two axioms, axiom 1 and axiom 2. If I is equals to j, if I is equals to j, then you apply axiom 1, and then you will say that, oh well, I'm writing at position I and reading at position J, this must be BI, and similarly here you must get an AI. Okay, so now you have AI and equals to BI, and then you have the same thing is saying not equal because I equals to J, so there you have a contradiction. Now let's look at other scenarios. If I is not equals to J, then what do? You can apply the axiom 2. Okay, when that handles the case when you writing on an array and reading at a different position, then you get the same value which you had earlier. Okay, so you get this guy is reading to BJ, you get BJ, and here you will get AJ. So we get BJ equals to AJ, and that gives contradicts. Therefore, you have a contradiction again. So you have two cases: I equals to J, you have contradiction. You have I not equal to J, then you have a contradiction. Therefore, whole formula is satisfied. The important bit to notice is when you started analyzing this formula, you didn't have any inclination you needed a case split, and that is the reason why it becomes exponentially hard problem, or it belongs to NP completeness, because you need to do case splits and figuring out where case split is needed